Hello, the talk is in 1 minute. Please take your seats. We'll have Marc Ruiz and Adria Julia presenting the project Starviewer. Please welcome the speakers.
Hi, I am Marc, and this is Adrià. We are from GLab in the University of Girona, and we are the developers of Starviewer. In 2004, a collaboration agreement was signed between the Graphics and Imaging Laboratory and IDI, Institut de Diagnòstic per la Imatge. In this agreement, GLab provides research knowledge and IDI radiology experience. And the objective of the agreement was to develop this. This is a Starviewer, which is a radiological viewer. Radiological viewers are essential in the medical imaging workflow. First, a technician acquires images in a medical scanner. These images are then stored in a central server called PACS. And then radiologists can retrieve these images through a radiological information system and view them in a radiological viewer. Like, for example, yes. The radiologist can retrieve these images from the server and view them in a radiological viewer. Okay. Like, for example, a Starviewer. The radiological viewer is the part that we develop. All this is governed by a standard called DICOM.
Okay. DICOM, it's the standard. It's a very thick standard which governs how medical images shall be stored, retrieved, saved, communicated, etc. And it's very extensive. And this standard gives also the vision of the world, which is the following. According to DICOM, in the world, there are patients in the world, okay? And patients usually go to the hospitals to take a study. And a study, for example, when you go to do a CT scan, okay? When you have a CT scan, you are being done in a study, okay? And in each study, you have different series. In each series, stores several DICOM objects, which may be images, graphs, encapsulated documents, etc. So, a viewer, the main goal of viewer is downloading these files and then display it to the radiologist. But not only this. If you have a series which is CT, which are, for example, slices of your brain, this is volumetric information. And from this volumetric information, you can make what's called a 3D volume. A 3D volume means that then you can do reconstructions and see your brain from different viewing angles, okay? In the case of a Starviewer, if we also have, for example, a PET image, which is from nuclear medicine, you can overlap them and then, for example, show the parts which are active, okay? This we will show in the demonstration. Okay.
Now, on the technical side of Starviewer, it's developed using C++11. We use several open source libraries, which make our life easier. Projects are based on QMake from the Qt framework. We have a multi-platform software, which runs on computer hardware, having at least OpenGL 3.2. It's multi-language, and in 2014 it was open sourced with a GPL license. The architecture can be separated in 4 main parts. At the bottom, we have the external libraries, which allow us to communicate with a PAC server or to read DICOM files from the local computer. Then we have the core, in which we have a wide collection of classes, which can be divided in 4 different categories or more. For example, we have widgets, which include basic 2D and basic 3D viewers, which allow you to see the images, but don't implement any interaction by themselves. We also have layout classes and hanging protocols, which is a special kind of layouts defined in DICOM. Then we have a collection of tools which are used to implement interaction with the basic viewers. So you can combine the tools you want with the viewers. Then we also have the input-output classes to communicate with the PACs, read local files, or communicate with local database. And the extensions engine, which allows you to create extensions, which we will explain later. Then the part that the user can see are the core user interface and the extensions. The core user interface includes several windows which are central to the platform, not related to any particular extension. For example, we have the study management window, the configuration screen, and several others. Extensions are one of the most important parts of Starviewer. They're intended to support general or specific workflows or to add new features to the platform. At this moment, we have 5 stable extensions, but new ones can be easily created. For example, here to the right, we have a screenshot of an extension which was created using just over 100 lines of C++. Now, extensions are implemented as static libraries. This has the downside that you must require Starviewer to add them, but you could have the advantage of using linker time optimization. In the future, we want to support both static and dynamic libraries. Now we'll show you a few images of the extensions and later a demo. The most important one is the 2D viewer extension. It allows you to see images in 2 dimensions and implements image fusion. The 3D viewer extension allows you to view the image using volume recasting or surface rendering. Both of them will be shown in a demo. The multiplanar reconstruction extension allows you to see images in 2 dimensions, but in a non-orthogonal plane. For example, here, there is an oblique plane which is aligned with a vertebra, which allows you to see the disc of the vertebra. Then we have the DICOM print extension, which allows you to send an image to a DICOM printer to have it in a film, like in the old days. And finally, a PDF extension, which lists the encapsulated PDFs in a study and lets you open them in the default PDF viewer. And now Adrià will show you a demonstration.
Okay, one moment. Here is the Starviewer main window, and one of the things that radiologists usually do is what's called a slicing. A slicing is changing the slice, okay? And as you can see, as I change the slice, this green line you can see here moves to show the slides you are seeing right now, okay? I will invert the colors because I think it will ease your task of viewing this, okay? Then, these are called reference lines. What we can do is taking several slices and generate one single image which summarizes them. This is called thick slab. So I put, for example, 120 millimeters, and as you can see, now we see the pelvis or the ribs, and we are visualizing this thick block of images, okay? I disable this because it is quite CPU intensive. Then there is what we explained before, which is the hanging protocols. Hanging protocols are templates that can be customized with XML files that if you are a doctor, you want to set up your diagnosis environment quickly. But in this case, I will put a manual layout of 3 viewers, okay? And in these 3 viewers, now I have, if I right click, I have the series 2, which is the CT scan, and here I have another series, which is the PET scan. This is nuclear activity, okay? And in this third empty viewer, I will put the fusion of these 2 series, okay? I will invert the colors to ease your task, okay? Then, if I move this here, we can see that there is a more active region, okay? And this is the fusion. One is the normal, this is the CT scanner, and this is the fused, this is the resulting fused image. Here I can change the color, for example, of this representation, and now it uses different color scale. What we can do also is doing measurements. For example, I can measure the distance from here to here, or I can do the calculation of several statistic values with a region growing technique, like here, okay? And it gives technical information we want to explain now. Now I will move to the 3D visualization module, which does 3D volume rendering, which is done usually through CPU, but it can also be accelerated using a GPU. I will choose this series, a moment, and I will apply this transfer function. It's the way you paint it, and I can rotate it, and here we have this poor man laying down. With volume, this is all filled, so I can change the opacity to see occluded parts, okay? Then, I showed what's called 3D volumetric data, but we can also have 4D volumes. 4D volumes mean that you have also time data. And this is the case of a heart magnetic resonance. One moment, I will open it here. Pam, pam. Okay, this is the heart of a person. I will put 2 viewers, and here I will put this image. Okay, I can slice. I am changing the slice. You can see the reference lines. This is one. I will invert the colors, sorry. Okay. One is one series, another is another series, but because series have metadata, we can know spatially how is located one respect the other, okay? And you can see the heart is moving. I will put play so you can see it better, how a heart is moving, and this is 3D. I am slicing, I am changing the viewing plane, and this is moving. So, well, here ends our demonstrations. If you have, one moment, where is it? Here. You can contact us with this mail, and you can find us on GitHub. And if you have any questions, no, okay. Question.
Which hospitals do you use? 1, 4, 10?
It is. They ask where it is used, this software. This software is used in research, especially in main hospitals in Catalonia, which there are centers that they do these CT scans, etc. Okay, and they use it there, and these are the people that paid for the development of this software. Okay, thank you very much.